Hello to everybody. Today's webinar is devoted to the seismic vulnerability of industrial structure, precast and steel. My name is Roberto Nascimbene, and I'm the CEO of Mosaic, whose let's say vision is to put the most advanced and recent developments in the field of structural modeling at the service of society at large through the provision of state-of-the-art consultancy to industry sectors such as engineering, construction, utilities, let's say insurance, legal arbitration, and so on. In other words, we believe and work towards what we say usually a model world. We have a team of highly skilled and qualified collaborators, all of whom with PhD or master degree on structural modeling and related fields, currently splitting their time between the provision of consultancy service and the engagement in research activity. And our company, Mosaic, works closely with its clients to analyze the behavior of different types of structure, let's say cast in place, precast, steel, timber, composite, infrastructures, bridge, tank, pipeline, subsystem like steel connection, by using advanced numerical analysis such as nonlinear, static, dynamic, time history, robustness, progressive collapse, impact, and blast and buckling. Today the presentation will discuss a general overview regarding seismic analysis and modeling technique about structures under an earthquake loading. It will be used Midas Gen for global analysis of building and Midas FEA for local advanced and nonlinear finite element analysis. Precast and steel structure will be presented, focusing on the main vulnerability and highlighting improvement in order to make the structure able to resist to an earthquake. I'm also, let's say, a member of the committee of the Eurocode 3, and this is the reason why Eurocodes will be applied to all the example shown later. Let us start with the precast structures and say that in Italy, the extensive use of reinforced concrete precast structure in the industrial field and in the service sector is the reason of the great development of one-story building, one-story precast structure, and of a more limited number of multi-story ones, whose demand is constantly increased in the recent let's say 20 years, 30 years. In the case of residential building, more traditional solutions like such as cast-in-place concrete structure and masonry ones are usually used for many reasons. We'd like to introduce the main information on typologies of precast structure and element behavior. The success of the technique of the prefabrication in Italy mainly depends on the speed of construction, on the relatively low cost, so it is quite understandable that the method of the emulation of the cast-in-place concrete envisaged by the modern design codes of the main seismic prone country never had particular success in the Italian context in the past years, because mainly it results in a partially increase in site labor and longer time of construction. The interesting solutions, let's say, developed worldwide in the past decades, among them, let's say, dry connection, are not usually currently used in Italy for the above reason, and because for precasters are usually looking for more, let's say, easy solution. Within this context, the main characteristic of our traditional reinforced concrete precast multi-story building, as well as the one-story structure, are precast socket column foundation connection, monolithic column fixed at the base and with corbels at different heights in order to support the beam at each story, shear resistant or partially flexural resistant beam column connection, which usually consists of steel elements without cast in place concrete, horizontal structural element simply supported or pinned to the column, panel supported by the structure or by the foundation beam. Particularly, it is, let's say, generally recognized that the connections are one of the weak points in terms of local resistance capacity and global seismic response. That numerical and experimental investigation on this topic are quite of relevant interest. In addition, the possible seismic retrofit of the Italian reinforced concrete precast structure potentially is a very wide worldwide topic, almost still entirely to investigate, especially for what concerns multi-story building. Let us investigate the most common element typologies, starting with the beams. Here we focus to the boomerang type of building and to the double slope beam here, and if we seismically focus on them, we can understand one important main vulnerability of this kind of beam that later we'd like to model. At the mid span, the height of the beam is a few meters above the top of the column. This means that the mass of the roof is moved up of many meters, and this will for sure change the period of vibration. Change means that it increases the period of vibration. This fact will probably reduce forces, but unfortunately it will for sure increase displacement. And we know that the seismic design is more a displacement-based performance design and not a force design. Common type of deck in multi-story structure and let's say roof element in a single story. The most used is the hollow core slab that we will investigate later. Common type of long span roof element representing a classical Italian production of roof beam that can reach up to 32-33 meters long. We must be careful for sure which kind of connection should be used at the end of the beam. Usually it is simply supported on a few centimeters, but we will see later. Common type of columns and foundation. Connection between column and foundation, we say that a very common solution is the use of totally or partially precast socket-based foundation. In case of a poor bearing capacity of the soil, traditional alternatives such as piles, beams, or reinforced concrete slabs are used anyway. A problem we should be considered with particular care is the connection between the reinforced concrete tie beams and the socket-based foundation. Because of the demand by precaster of simpler techniques without cast-in-place concrete, due, as we have seen before, to the increased use of unskilled labor and the increasing in time. In addition, despite the simplified design method, the tie beams usually are also the support for the vertical panels. Therefore, they are not usually aligned with the column, and this means that we need to add mass to the column. We have typologies of top of the column, flat, fork, and this will be really interesting in the next stage of modeling technique, and continuous column from the base to the top of the building. Non-load bearing facade elements are intended to contribute to the architectural effect of the construction through shape, color, texture, quality. Thermal and sound isolation is achieved by the insertion of light, expanded foam or mineral fibers materials into the facade. The orientation of the infill panels can be important in the seismic response of the structure. If they are horizontally oriented, the entire mass is generally distributed on the height of the column, and as we told before, mass on the column means modification in the period of vibration. In case of vertical orientation, they are horizontally constrained at the top, but their weight is directly distributed to the foundation in a certain percentage of the total weight of the panel, so it can be reasonable to consider only a part of the mass linked to the structure. Then, more detailed information about the characteristic of the most common structural typology should be defined. These main common structural typologies, which cover a very large percentage of the Italian production, was achieved from an investigation of the available Italian literature and directly from precasters and designers for more than 500 of buildings. Similar research was useful in order to determine the most significant techniques used in the seismic zones to connect the element. Let's start with the one-story industrial building that should be usually divided at the top of the slide between two typologies. The first is a more traditional one and very frequently used. Substantially consists of a series of basic portal frames parallel to each other. Each portal comprises, let's say, two columns fixed at the base, and the roof beam usually simply supported by the columns or characterized by shear resistant connection. The stability of the system is totally based on the cantilever action of the column and on the good response of the column foundation connection. The maximum span length in seismic zones is less than 27-28 meters, and the maximum distance between the portals, which depend for sure on the span length, is usually 12-10 meters. One more very common typology characterized by longitudinal primary intermediate beams, which carry the main roof beams, is used in order to cover larger span length. This, let's say, second solution, in comparison to the first one, however, is less efficient in terms of seismic response because of the greater weight mass of the roof being equal to the number of columns. Second typology is multi-story building. Multi-story structures are characterized by monolithic columns fixed at the base and single span beams with pinned ends, not always provided along the two directions of the horizontal plane. Common beam cross-section are rectangular, L-shaped, as we have seen before, or for example, inverted T-shaped. Hollow core or double T floor slab are by far the most common type of floor slab in this kind of buildings. The height is usually up to 3, 4, no more than 4 story, and can be limited by the stability problem or excessive flexibility due to the fact that the columns are fully continuous starting from the socket to the top of the roof. The plastic hinges are for sure expected at the base of the structure, except for particular cases such as sudden interruption of the longitudinal reinforcement along the height of the column. Again, we can say that in a precast structure, the characteristic of the connection, which are strength, stiffness, ductility, energy dissipation, capacity, post-yielding stress degradation, and more, between the structural elements determine the global response of the building. Let us try to demonstrate this by considering two frames. On the left, a multi-story frame structure with fixed column at the base and pin-end beams, a classical precast building, and a multi-story frame structure with monolithic beam column connection, reinforced concrete frame on the right. What are we going to expect is the right question. Different displacement for sure, different actions, different behavior, as we can see here schematically, but let us use Midas Gen to model and to demonstrate this global consideration. Let us consider the two frames, the precast with pin-end beam and the reinforced concrete with a fully connection, two frames that possess the same geometry, the same sections, the same weight, the same masses, same loads, live and permanent, and in general, I mean the same design, and we apply the same external forces, let's say in a pushover fashion. Clearly, the left frame, after a Midas Gen analysis, the left frame with this continuous connection is absolutely more flexible if compared to the fully continuous connection on the right. We have to remember that in the finite element code, the stiffness matrix depends for sure on the elastic modulus Young, the inertia of the section, the length of the element and the area of the section, but also on the degrees of freedom. Could be fixed or simply supported or hinge, and these change the global behavior of the building itself. So the left frame is absolutely again more flexible than the right one, the fully continuous one. Now, having used Midas Gen application, we can for sure recognize that poor details in connection are the most common reason of non-adequate seismic response. In particular, poor detail connection of moment-resisting frames can result in brittle failure of the steel reinforcing bar near the welds. In addition to this consideration, a large number of collapses have been observed in past seismic events in Turkey 1999, in Italy 2012, where several precast structures collapsed because of mechanisms related to loss of support, poor detailing of the connection, poor reinforcement, have been shown. In particular, the characteristic of very common connection used in the Italian constants, which influence the global seismic response of the structure in terms of strength, stiffness, and ductility and energy dissipation, may be seen here. connection between saddle beam and the top of the column, one-story structures, means dry connection with use of one transversal ungrouted steel bar on the top left of the slide, diameter 24-30 millimeters, tightened with nut and washer, or a maximum of 2 grouted vertical steel pins. Although the pins are tightened into steel blocks, which are anchored into the concrete element by welded bent steel bar, the tensile resistance of the connection can be considered negligible because of the very small length of the pins. Second type of connection is connection between beams and corbels in a multi-story structure. Dry connection with one or two vertical threaded steel bar fixed to the corbel by casting steel sleeves and tightened to the beam by nut and washer. Rarely and only in seismic zone, the vertical hole in the beam, which is usually obtained by a steel box with hollow rectangular cross-section, is grouted. Third type of connection, the roof beam and the double T beams, are usually connected by L-shaped steel plate, reinforcing steel bar and cast-in-place concrete. Connection between panel and structure. Usually the horizontal panels are supported by steel corbel, while the vertical panels are directly supported by the foundation beam or tie beam, and in both cases the top connections are usually used to prevent the overturning of the panel itself. Let's move to recent major earthquakes in the Italian context, in the Italian territory, that these quakes have reaffirmed the seismic vulnerability of precast industrial building, typical of past Italian building practice, highlighting structural vulnerability observed during previous events and primarily related to the transfer of horizontal forces between structural and non-structural elements. An intrinsic, let's say, lack of shear and ductility capacity has been observed in simply supported beam to joist and beam to column connection, primarily constituted by vertical steel dowels or relying on shear friction with or without pads, like, let's say, neoprene pads. These connections were designed neglecting seismic loads, and their premature failure was observed during recent seismic events to cause a loss of support of beam element, such in this figure, owing to the relative movement of element and the collapse of part of the building, primarily the roof. Seismic displaced demand of the industrial building under consideration is larger than traditional reinforced concrete frame structure, owing to their very higher flexibility according to both higher interstory height and to a cantilever static scheme. Furthermore, this high flexibility may also result in displacement incompatibility between structural and, as we can see here, non-structural infill panel, non-structural element, such as precast cladding panels, causing for sure their connection premature failure. The most severe damage occurring during Emilia earthquake was mainly associated with the structural element loss of support and consequent falling, because the beam to column and roof to beam connections lacked mechanical devices, as we can see here, as seismic load transfer mechanism. Another frequently observed failure typology is the, as we have seen before, collapse of cladding panels consisting both of brick or light brick masonry and precast reinforced concrete element. Concerning the former, traditionally used in building, let's say, of category A, incipient collapse was observed to be associated mainly with high out-of-plane slenderness because no lateral restraint was provided in correspondence with columns and reinforced concrete spandrels. In structure of, let's say, general category B, the observed falling of horizontal and vertical reinforcing concrete precast cladding panel was clearly related to failure in the mechanical connection, typically anchor channel and C-shaped or L-shaped steel profile to the supporting column and or beams. In fact, let's say, these devices were designed to sustain primarily vertical gravity loads and to avoid overtuning of the panel as a consequence of low out-of-plane horizontal action such as wind loads. During an earthquake, this kind of connection needs to accommodate high relative displacement and rotation because the displacement and rotation demand are concentrated at the connection level, owing to its lower stiffness compared to connected precast element. Here is a Midas Gen model of a two-story frame building where it is really important to create the real building model, the real structural model. This is the reason why in case of a wall we can adopt two different strategies of modeling. The first one is based on the equivalent beam element, which has the same section and inertia and material of the real wall. Important in Midas Gen is the tool that make the practitioner able to represent the real behavior of the wall by imposing that the slave nodes behave as the master node. This is for sure a better way to model the wall than the ridged link, because we know that the ridged link make the matrix, the stiffness matrix, less stable. The typology of modeling technique used by Midas Gen, master slave and node slave, make the stiffness metric numerically more stable. A second approach I like and more close to the reality is using shell elements. Important to use to select thin shell element, because thin shell is based on the Kirchhoff theory, and this means that we have a thickness of centimeter and an area of the panel of square meter. So the panel is thin. If we use thick element like Timoshenko theory, we follow the shear, the strain, the shear on the panel itself. Using the thin shell element, we can obtain the real distribution of the stresses along the wall, for example, that can be used for distribution of the reinforcement, and the real geometry representation of the full building. Let us see a comparison between the two models in after running an analysis, eigenvalue analysis in Midas Gen. With only 12 modes of vibration, we obtain approximately 10% of participating mass. That's a good result. And in the next slide, the first three modes of vibration using the shell element are perfectly in agreement, perfectly agrees with the beam equivalent model. It is important to note that the first period of vibration using shell element is a bit, but a bit means less than 0.1%, then the corresponding period of vibration of the beam equivalent model. This means that the shell model is more rigid than the beam model, and that's fully true, because more higher is the degree of the discretization, more rigid is the model. From beam to shell to brick, more rigid is the numerical model. If we move to a torsional building, a building with high torsional effect, we can apply both the same modeling of before, the beam equivalent model, representing with master node and slave node the geometry of the structure, and a L-shaped wall on a corner may be also modeled using a shell approach. Again, we can compare the eigenvalue analysis done with Midas Gen, and the results are for sure in very good agreement as before. The shell model, it seems to be a bit rigid, but that's a good result, that's fully true. Moving from a single wall to a stairwell global building, we have to ask if we can represent such kind of behavior. If the stairs is rigidly and fully connected to the stairs, to a column, in case the building is originally designed for gravity load, it happens that a high unexpected value of shear due to the quake is capable to highly damage the column as observed in this slide. In this case, we need for sure a more advanced Midas Gen numerical model as the one herein proposed. The equivalent beams are used for the four wall representing the four wall of the stairwell, whilst the rigid link are used to represent the real geometry along the wall, and the membrane element are used to model the landing. Using this kind of behavior, we are able to fully represent the connection of the stair with the column and the shear failure using a Midas Gen model. Moving from a wall, stairwell, global building to single local element, let us compare two different modeling techniques that can be used in Midas Gen. The first one on the top easily put the beam and the roof center line on the top of the column. The second one on the bottom use rigid link to put the real elements in the real position. This is for sure the best model we can do using the advanced link procedure in Midas Gen, because we can place the real mass at the real position by giving the building the real behavior, period of vibration and flexibility. And we know that the real mass in the real position will give us the real flexibility of the building, and that's a key point in a quake engineering. If we have an inclined beam, we have to put the double T roof at the top of the beam in the right position using end offset, using rigid link, or if we need, using elastic link if the support requires it. Furthermore, in order to be able to represent the shear connectors of the roof to the beam using still L-shaped link, we may refer to the approach proposed by Midas Gen in the next slide, where two different schemes may be used. One on the left that is simply supported, and the second on the right that is partially fixed. Two different response spectrum analysis may be run in Midas Gen, and two different spectrum in output may be obtained, in the sense that with a simply supported connection between roof and beam, we obtain a more flexible diaphragm. With a partially fixed connection between beam and roof, we obtain a more rigid, more stiff structure. Again, we can one good question, let's say, that can be solved using Midas Gen is how many connectors should be used and how they influence the behavior of the roof. Using Midas Gen model, we can perfectly define if the roof is rigid and can be classified as a rigid diaphragm, or if the roof is flexible and can be classified as flexible diaphragm. We know that in the Eurocode and in many codes all around the world, the two behavior are different. Here again, as we have seen before and as we can see in this picture, the fork on the top of the column will contribute to the global behavior of the building. The fork at the top of the column play an important role that sometimes must be modeled in Midas Gen, and here is a model used to take into account the fork by using elastic, rigid links, beam and node. Here is a full, complete representation of the full building, where, as we can easily check, all the previously defined modeling approach in Midas Gen have been completely included. And for example, we can show here the behavior of the building model with Midas under a quake event, an accelerogram that we can see on the bottom left side of the slide. For example, by checking the P ground acceleration of the accelerogram exactly here, we can see the cantilever action on the full building. This is a single story with on the right side a part with offices building that move from one story to multi-story structures, and we can easily check the strength, ductility demand, and stiffness, and in general earthquake requirements in a structure after the application of a time history analysis. Let's move to more refined analysis from global, let's say, to local, and that are usually required in order to capture the real behavior during an earthquake event of the L-shaped steel plate, for example. In this case, a more local Midas FEA model could be used using single shell element. Using this approach, we can see exactly all the local collapse mechanism of the steel plate in case, for example, of shear, in case of tension traction, and in case of compression. More refined information could be obtained using Midas FEA. If a window, non-structural element is placed on the roof between the roof beam a refined model including the link interaction should be used. In this case, for example, this is a second case of window. In this case, we are able to capture a flexible roof behavior with a classical non-synchronous behavior after an earthquake. This mechanism has been greatly observed, as we can see in the picture, in previous earthquake. It gives rise to a loss of support, as clearly seen in the field observation during the Italian earthquake. As a next step of more refined analysis, here is a model in Midas FEA that can make us able to observe the formation of a plastic hinge at the level of the connection between a beam and the column. Next, we focused on the global behavior of a precast structure and on the local behavior of the element. And right now we can focus on the use of precast concrete in flooring system. The use of precast concrete in flooring system is a widespread practice in many countries, and precast pre-stressed hollow core units are commonly spread products of precast company, finding for sure wide application in building construction, particularly as floor and roof components, as we have seen before. Short construction times, high level of quality, and consistent reduction of cell weights are achievable, allowing manufacturers to cover span up to 20 or more meters. The upper surface of the hollow core slab is usually leveled with a cast in situ concrete topping. Normally, for long spans, advantage is not taken of this topping layer as a composite construction because of the uncertainty concerning the bond strength between the precast and the cast in situ concrete. Proper shear strength at the interface is required for the composite action. The horizontal and vertical shear strength of the joint between, let's say, adjacent hollow core units has to be high enough to transmit the forces due to the horizontal diaphragm action. Through the years, 200 and 265 mm thick units, characterized by cross-section with circular voids, were replaced by deeper units, 320, 370, 400, 500, presenting cross-section with non-circular voids. Many past experimental data have been examined to obtain an experimental database of single span and simply supported isolated precast pre-stressed hollow core units loaded with, as we can see here, transverse and uniformly distributed line loads, highlighting web shear failure mechanism due to short development length and lack of shear reinforcement. We observed 49 specimens that were characterized by 6 nominal slab depths, 5 hollow core shape with circular and non-circular void and different voids ratio, and several pre-stressed steel trends arrangement and level of initial pre-stress. To quantify the effectiveness, 3 commonly known codes prescription: Euro Code number 2, American Concrete Institute Code, Canadian CSA Standard Association, and as well as a research approach against web shear failure mechanism were adopted to predict the previously defined experimental database. Here is the scenario. The scenario depicted by analytical prediction suggests the need of a detailed campaign of numerical analysis and for this detailed comparing of numerical analysis, we use for sure Midas FEA, in order to address and to investigate the effects of the hollow core shape on the shear response of such members. To properly reproduce the experimental test setup, a refined nonlinear three-dimensional finite element model using Midas FEA based on nonlinear advanced fraction mechanics were developed and monolithically loaded till the brittle web shear failure mechanism is reached. 9 models, 9 specimens whose main features are presented here have been considered. In particular, let's focus on the fact that for 320 mm this slab, 3 specimens have been selected, 2 characterized by non-circular and 1 by circular voids to quantify the hollow core shape influence on the shear strength capacity for members with similar depth. Similarly, 2 400 mm deep units have been analyzed, since they evidence non-circular hollow core shape with various levels of irregularity. Next slide is an example of our three-dimensional model using Midas FEA, using 2 different types of mesh, depending on the shape of the void in the hollow core system. To predict the brittle web shear failure mechanism, the total strain crack model, developed along the line of the modified compression field theory (MCFT), was adopted. And this modified compression field theory with the total strain crack model is implemented in Midas FEA, that it is very efficient. The classical von Mises yielding criterion with strain hardening was used for prestressed steel strands, represented, as we can see here, as embedded elements. 2 types of prestressed distribution, linear, according to code like ACI or CSA, and parabolic, according to the scientific literature, were considered to evaluate their influence on the shear strength. In this case, no interface element were introduced to represent strength concrete interaction, since simplicity captured by an equivalent pre-stress distribution. The smeared fixed cracking constitutive law assumed for concrete with an exponential softening decay curve and the Torsional model for uniaxial tensile and compressive behavior has been introduced in Midas FEA. Confinement effect was neglected, while full shear retention and lateral crack effect were potentially accounted using Midas FEA, as well as inward slippage of the strength. Newton-Raphson iteration scheme was adopted with an energy normalized convergence criterion. 6-node brick elements were used, and mesh sensitivity was investigated by doubling the extruding offset. For each specimen, an equivalent strip of the hollow core unit was modeled to evaluate the effectiveness of these assumptions. Here, a numerically predicted web shear failure mechanism and the numerical crack pattern at ultimate condition are shown. Furthermore, it has been shown the evolution of principal tensile and compressive strain distribution. The principal tensile strain directly governs the failure mode and the presence of a variable inclined stratum tie, whose width and inclination angle evolves during the monotonic analysis, and it is clearly evident. Tie width reduced as the imposed vertical displacement increase, reproducing the actual shear stress flow characterized by peaks placed in correspondence of the bottom side of the cross-section rather than at the level of the centroid. A brittle web shear failure mechanism results from an inclined diagonal crack. This can be observed using the total strain crack approach, which for this specimen, with a sharp web width variation along the depth, almost linearly propagates from the support to zones upper than the centroidal axis at the distance of about 2 cross-section depth. This was possible due to the capability of the total strain crack approach in Midas FEA. Accordingly, a diagonal strut whose width increases as the imposed vertical displacement increases connects the transverse line load and the support. This failure mode results into an incipient change in the shear stress distribution localized at a distance roughly equal to the hollow core depth, where the maximum tensile strain overall the whole member is undergone. Let's move to the second topic of this presentation, almost at the end, on steel structure. Concentrically brace frame, concentrically steel brace frame are commonly used for seismic design in high seismic areas due to their high stiffness and strength, when usually compared to moment resisting frames. In the current design practice, concentrically braced frames are designed and detailed to highly dissipate energy through brace yielding in tension and inelastic buckling in compression under the strong shaking of an earthquake. In order to dissipate energy through this mechanism, it is for sure essential to ensure that premature failures in the connection are deeply prevented. Many advanced finite element models using Midas FEA have been done in order to check this mechanism at different levels. Gasset plate connection and braces are shown in this slide. Gasset plate at the top and buckling of the brace at the lower level. Here, the ability of the Midas FEA model to reproduce the experimental behavior is clear. An appropriate detailing of the clearance at the gasset plate is fundamental for the brace to accommodate buckling in the out-of-plane direction by, let's say, forming a plastic hinge at the gasset plates rather than at the brace end. And that's a key point in the performance-based seismic design of structure, usually called hierarchy of resistance. To investigate the performance of the brace, a model has been built using Midas FEA, as can be seen here. All elements were modeled using 4 node shell elements available within the Midas FEA program, and shell elements are capable of taking into account the in-plane membrane and the out-of-plane behavior, bending and shear of the region model. The foam Mises yielding criterion was adopted with bilinear isotropic hardening to represent the material non-linearity. Here is the result after a compression application of the load. Then tension goes ahead, and here we can see in a good fashion the shape of the deformed tension of the brace that start to concentrate in the middle, the deformation, and the last cycle will kink the behavior in the middle zone of the brace, and this is usually called a buckled of the rectangular hollow section core of the steel braces. Then we can move to the next slide, where we can check that the locally buckled region is for sure compared and equal to the one observed in a past experimental program, and we can for sure close the presentation by watching how Midas FEA is able to reproduce the experimental test. Here it is clear that superimposing the Midas FEA numerical model with the experimental data available, the Midas FEA model is able to reproduce the initial stiffness, the stiffness degradation during the evolution of the pushover analysis, is able to represent the strength and for sure the ductility, the damage scenario, and by considering globally the cyclic behavior, it is also able, Midas FEA, to represent the energy dissipation of the full cycle. I wish to thank all of you for listening me during the presentation, and do not hesitate to contact me using my mail in the first slide if you have any question on this presentation. And thank to everybody.